We'll continue with wideband amplifiers today. Okay, so we looked at some 5 or 6 different kinds of single stage widebanding techniques. We'll just look at one last one today, okay, which is called the zero peaked amplifier. Okay, so what is the fundamental problem? You're having the pole which is which is dominating your roll off is actually your RL times CL. Okay, so what we'll do is we'll add an RSCS here. So what we'll see is this RSCS actually produces a 0 in your transfer function, and you can try to cancel RLCL pole with RSCS pole, okay, to make a wideband amplifier. So what is your the impedance at the source is nothing but RS over 1 plus SCS RS. Okay, impedance at the load again is RL over so if you plot the effect of GM, okay, which is GM of S, is nothing but GM over 1 plus GM ZS. So you can put in this expression, and you can rewrite it in a slightly different form. Okay, so we'll put in this expression here, take 1 plus CS to the top, and we'll do a little bit of manipulation, and we'll rewrite this as no approximations. Okay, so this is the 0 you wanted. Okay, so you can rewrite it in this form. So now you're going to make a small approximation. So first of all, you're going to approximate that GMRS is much greater than 1. Okay, so in this term it just becomes 1 over GM. What is GM over 1 plus GMRS? Is just your DC transconductance, right? GM of 0 times 1 plus SCS over GM. Okay, so your voltage gain is nothing but your GM of S times ZL of S is GM 0 times sorry. Okay, so this is AV of 0. This is your DC gain. Sorry, times okay, so this is the pole and 0 you want to cancel, times this is your, now once you cancel those two, this will become your dominant pole, SCS over GM. parasitics of the transistor, you are assuming that, okay, you are assuming that of course that CS and CL are much larger than your capacitances. Remember that CL is, let's say it's the load capacitance, which could very well be the input of a similar amplifier. Okay, that will be CGS or CGG actually, CGS plus CGD. Okay, that will be much larger than CDB. Okay, so we are just neglecting it for now. In reality, you are right. Those components will also give you either higher order poles, or they'll pull in these poles in some way. One of those two things will happen. Okay, but for now we'll just neglect it. We'll just assume that CL is dominant. Okay. So you can, plot out all three of these to find out, get a graphical view of what is happening. Obviously GMRL is constant with frequency. Okay. So the 0 is going to go like this, and the pole is going to go like this. Okay. If they exactly cancel, then the overall transfer function is just going to look like this. Okay, it's just going to be flat. And if you look at the third term, which is this guy, so it happens that you have a single pole at SCS over GM, so it goes like this. So obviously the overall transfer function will look good. Overall transfer function is going to look very good. Okay. Okay, this is your AV. Actually, AV of omega. So instead of being limited by this pole, you are now very far out, assuming that GM is very large. Okay. Okay, so that kind of does it for your single stage amplifiers. Okay, so if you are for a single stage, you can maximize your bandwidth. Okay, how about, let us say, instead of being limited, so far, like he said, we have not considered the parasitics of the transistor itself. Suppose what happens if you just increase the FT of the device itself? So there may be many cases where you might want that. Okay, because all things being the same, if you improve the FT, you can improve the overall performance. Okay. Omega t 2 pi ft was GM over approximately CGS plus CGD. Okay, so this is assuming that the input point is the has the maximum dominant capacitance, so it is nothing but GM over Cn. Okay, so now let us say we take a single transistor and you increase your current. Okay, what happens? So we know that GM goes as square root of I. Okay, so if you double your current, you will get a 1.4 increase in FT. Okay, that is assuming a long channel transistor. Okay, for long channel. If you have a short channel, you will probably get much less than that. Okay, because you're going to have velocity saturation. Okay, so let's consider what are called FT doublers. Okay, some very simple circuits to improve the overall FT response. The simplest FT doubler is actually your differential pair. Let's call this. Okay, so now what you are doing is you are actually doubling your current, bias current. So let us say earlier for a single transistor the bias current is I0. Now you are going to make it 2 I0 because you want the transistor, let's say the sizes are also the same. Okay. What is your effective GM? It so happens it is the same as the GM of the transistors, right, of the diff pair, each of the diff pair devices. What is Cn? Because you have the two CGSs in series. Okay. Okay, so effectively you have doubled your FT of the overall pair. Okay, so this is actually a very simple way. So effectively what you are doing is, from each differential path you are getting GM. So effectively you are almost doubling your overall GM, right? Effectively you can think of it that way also. Okay. So your FT is doubled in this circuit. But in many cases you may not be able to do differential signaling, okay, because it is quite inconvenient. There may be some cases where you might need it, okay. So you want a single-ended FT doubler, okay. So what you do is you take the same guy, and what you are going to do is you are going to reverse the gate and source connections, okay, which means the actual current the signal current gets reversed in phase, and then you can actually sum the outputs instead of taking the differential output. So it looks something like this. Okay. So you are going to, so this is your effective gate, this is your effective drain, this is your effective source. This is actually like a Darlington pair. I don't know if you have seen, remember from your analog circuits course. Okay. Except that the difference is you are going to bias the second transistor at the same bias current as the first one. So the simplest way to implement this is like this. Okay, so the current source is just done as a diode. So in other words, it just mirrors the I bias over to the other side. So this is called this is called the Battius FT doubler. Okay, there is a scientist called there's an engineer called Carl Battius at Tektronix. Okay, he invented this actually for a bipolar transistor, but you can do this do a similar thing for MOSFETs. So what do you have? Let's call this 1, 2 and 3. What is Cn? It's approximately CGS1 okay. Now you actually have an extra capacitance, extra CGS from your diode connector transistor. Okay, so which means your actual FT will get only approximately 1.5 times instead of twice, but it's still pretty good. Okay, mainly because these circuits don't depend on, whether you have short channel effects or not doesn't directly matter. Okay, if you just take a single transistor and double the current, you'll go more into velocity saturation, whereas in this case you don't have that problem directly. Okay. Okay, so that is for FT doubling. Increasing them, there are a couple of other circuits. Okay, we won't worry too much about it. So now we have considered a single stage amplifier. Now suppose you want to get an overall, a very large gain. Okay, you won't be able to, and you want large bandwidth. Okay, we know that a single amplifier has the gain bandwidth product. Okay, which means if you get large gain, you will get low bandwidth and vice versa. So now you want to get both large gain as well as large bandwidth. The easiest way to do that is to cascade many stages. Okay, so let's look at that. Okay, so let's say we have n stages. So what we are going to find out is, we are going to find out the characteristics of an n stage cascade, okay, in terms of gain, bandwidth and so on. The main reason we want to do that is, if you want to achieve a particular overall gain, what is the optimum number of stages, what is the optimum bandwidth of each stage, these are all things you need to know. Okay. And we are going to assume that all n are identical and have a single pole response. Okay. So we are going to assume that the 3 dB cutoff frequency is omega naught and your unity gain frequency is omega u. Okay, for each amplifier. So for a single stage, it is just A naught over 1 plus S over omega naught. So the cascaded transfer function is okay, it's just A naught over 1 plus S over omega naught whole power n. Okay, so now for this cascade we want to find out the 3 dB bandwidth. Okay, how do you find this out? You just take h of j omega, okay, you equate it to 1 over root 2 times h of 0. Okay, so you're going to do the same thing for this. So let's call the 3 dB bandwidth as omega naught n. Whole power n. Okay. So the overall bandwidth for an n stage cascade is nothing but omega naught times root of 2 power 1 over n minus 1. Okay, that's very easy. So you just A naught gets cancelled. 1 plus omega n or omega naught whole squared is nothing but 2. Okay, whole power n is nothing but 2. Okay, and you can also rewrite it in terms of omega u. Remember that A naught omega naught is omega u, so you can also write equals okay. So the first thing you notice is bandwidth shrinkage. Okay, for each amplifier it is omega naught, but now your overall bandwidth is actually smaller, okay, by this factor 2 power 1 by n minus 1. So let's say you have a very large number of stages, bandwidth tends okay, so that's omega n actually tends to 0, okay, but your DC gain tends to infinity, okay, that is obvious. So now we have it in terms of 2 power 1 over n. So let's try to find a better approximation for it so that we can see. For example, we want to see whether it's linear, square, and so on, right? So if you have certain n stages, we want to find out how it goes. So let's try to find that out. So we're going to write 2 power 1 over n as okay, e power ln of 2 power 1 by n, which is e power 1 over n ln 2. So now what we are going to do is we are going to expand it as a series, and we'll just take the first two terms. Okay. Assume that n is very large so that the other terms are negligible. So you just get 1 plus 1 over n ln 2. So what is this? So inside the square root you have 2 power 1 over n minus 1, which is just 1 over n ln 2. Okay. So which means for large enough n, your bandwidth, overall bandwidth is going to go as 1 over square root of n. Okay. How about the gain? So you want to find out the optimum gain per stage, which means the optimum number of stages. Okay. So now that you know this, you found the expression for omega on, you can do d omega on by dn equals 0. Okay. So remember that it is this. So we're going to write it as omega a naught is nothing but, let's say the total gain is a tot whole power 1 by n, because that a naught is not an independent factor. Okay. So this is the function you want to maximize. Okay. So you can do this and find out, so you'll get something like this. Okay, you can do some algebra and you get n naught is ln 2 over okay. You get some expression like this after some algebra. And again you can make an approximation for this, which is, let's assume you want a very large enough gain. So this second term is very small. So ln of 1 plus x, you can just say it's approximately x. Okay. Okay. So your actual optimum number of stages is nothing but 2 ln the total gain. Okay. So now you want to find out the optimum gain per stage. Okay. Let's call it a opt. Is nothing but a tot whole power 1 over a naught. Okay. Again we'll rewrite it like this. Okay. What is ln a tot over n naught? Is nothing but half. Okay. So you're just going to put this equation in here. So your actual optimum gain per stage for a very large number of stages is actually root e. What is your optimum bandwidth? So you just put in A dot whole, you just put in n equals n naught inside the equation. So this A dot over 1 over n naught is nothing but root E. Okay. Again, you are going to write this expression, okay, as sorry. Okay, you can rewrite it like this. Okay, so this is an expression for the optimum bandwidth. Okay, so the first thing you notice is, remember, for a single stage amplifier you had the gain bandwidth product was constant. Here what you actually have is bandwidth times okay, here actually you have bandwidth times root of ln of A dot, which is the constant. Okay, because once you choose omega u, everything else are just constants. Okay, actually this you can write it as, I think 0.357 omega u over, okay. So the first thing you notice, and this actually shouldn't surprise you, because your gain bandwidth product is constant always for a single pole amplifier whenever you have a dominant pole. Okay, this is actually a multi-pole system once you start cascading. Okay, so your gain bandwidth product no longer has to be true. And the other thing to notice, because it depends on the log function, okay, if you need to extend your bandwidth by a large enough amount, your gain doesn't change that much because it's a logarithmic function. Okay, in that case, since it is linear, 1 over A times B, if one increases by double, the other has to fall by half. Here the trade-off is much more relaxed. Okay. Okay, so now we talked about the gain bandwidth delay trade-off. Okay, so now there are certain applications where delay may not be very important, and especially in cases of one-way communications, like for example television. Okay, somebody else is transmitting, you are receiving. If there is a certain amount of delay, you won't notice it. Okay. Okay, so now there are certain cases where you can actually trade off your gain versus delay, okay, and get a really wide band amplifier. So we are going to discuss that now, okay, which is the distributed amplifier. Okay, it's also called the traveling wave amplifier, and you'll see in a minute why it's called that. So the general structure looks like this. So let's assume you're going to take what is called a tap delay line. So it's basically a transmission line. You're taking periodic taps across it such that each section has equal delay. Okay, and the characteristic impedance is Z0. Okay. So in this case, we just consider a 3-stage. Actually, so you're going to take a second tap delay line and put it at the gate of the transistors. This is your Vn. Okay. The main idea is this. Okay. So if you, let's say you have a certain, let's say at the input you can give a step input. Okay. After a certain delay, it arrives at node 1. Okay. Gets amplified by this amplifier and goes to this node. Actually, let's instead of numbers, let's call them A prime, B prime, C prime. Okay. So after one delay, signal arrives at A and then gets amplified. So the GM of the transistor turns it into a current. Okay. So the current will be GM times the input voltage step, and that gets multiplied by the impedance looking in. Okay. What is that impedance? It is nothing but Z0 over 2. Okay, you have Z0, you're tapping into a transmission line, so you have Z0 on one side, Z0 on the other side, so the input impedance is Z0 over 2. Okay, so the actual gain of this stage, one stage, is nothing but GM Z0 over 2. Okay, what happens after one more delay? The same input step arrives at B. Okay, the second transistor converts that to a current, and that gets converted to voltage, again equal to GM Z0 over 2 at B prime. Now what happens to the signal which was created at A prime? Assuming that the delays of the two transmission lines are identical, the first wave actually appears here in complete coherence with the second wave, and they'll add constructively. Okay. Similarly at the third point, so you can keep having, almost, okay, you can keep having a large number of stages. So the overall gain of, if you, let's say if you have an n stage, okay, distributed amplifier, is nothing but n times GM Z0 over 2. Yes, of course, that is definite. Okay, so you're assuming that the delay through the okay, what would that delay depend on? You're assuming that the frequency of interest is much larger than the FT of the much smaller than the FT of the transistor. Okay, so obviously the delay from here to here will depend on the FT. Okay, so definitely at lower frequencies that is valid. As you go higher and higher, you will get some amount of delay through the transistor, so you'll have to compensate for that if you want. But the difference is, even if there is some delay, you will still get a significant amount of gain even at FT. Okay, because you are adding up so many gains. Okay, you will still, so the advantage of this is that it's actually a really wideband amplifier. All the way up to FT you can get some significant amount of gain. Okay, that is the most important characteristic of this amplifier. The other thing, if you have n stages, your voltage gain is actually proportional to n. Okay, so it's linear. Overall gain is linear with n number of stages. So obviously this means that you can get gain even at FT. Okay, you can actually get some amount of gain at Ft. Okay, so now coming to the details. Obviously, you are assuming there are ideal transmission lines. Okay, we know that. Okay, so ideal transmission line, you can represent it as the RLGC model, distributed RLGC. Okay, where they are all per unit quantities. Okay, now remember that here you have CGS, here you have CDB. So the transistor capacitance is not symmetric between the gate and the drain. And remember that you want equal delays on both the lines, which means you need to be careful. So the two transmission lines will never be the same, even though in an ideal case you would want them to be the same. Once you start taking into account transistor parasitics, you will have to adjust. So you can absorb the CGS into the shunt C of the transmission line. You can absorb CDB into the shunt capacitance of the transmission line on the drain side. Okay, except that now those two transmission lines will be slightly different. Okay. Okay. Now the other thing to know is that in many cases you may not be able to do a real transmission line. Okay, the reason is at the frequencies we are interested in, which is a few gigahertz or maybe few even tens of gigahertz, the actual wavelengths will be pretty long. Okay, will probably be in millimeters or maybe tens of millimeters even, and you may not be able to create such a long transmission line. So you can actually use lumped LC models. Okay, in other words, you want a certain amount of delay. Okay, so that's what you want. You want equal amounts of delay. If you actually give an LC that actually gives you lumped LC quantities, actually give you enough delay that you need at the frequencies of interest. So you can actually use lumped LC for these transmission lines. Not models, lumped NC sections. How do you choose L and C? So the first thing you have to remember is, in the ideal case, the transmission line is lossless, but you know real transmission lines are always going to be lossy. Okay, in fact that itself should tell you that you cannot just randomly keep increasing the number of stages. Okay, because in the ideal case, if you increase the number of stages, it will go as n, but in reality, remember that along a transmission line, your voltage wave, if you have some attenuation, the voltage actually goes as an exponential. It exponentially decays along the transmission line with alpha, right? So now there will be a certain optimum number of stages. Okay, so beyond which you will not get any gain at all. Okay, the input voltage will slowly die out as you go along the transmission line. Okay, and the way you choose L and C, remember that your L has losses, C has some losses. So the way you choose L and C will depend on that. Okay. The other thing to remember, if you take an ideal transmission line, okay, with per unit quantities L and C, it actually has a delay which depends on LC, but actually has no bandwidth limitation for an ideal transmission line. Okay, but if you have a real transmission line, it will have the bandwidth limitation as we just saw. So once you have a bandwidth limitation, you want to choose constant group delay. Okay, which means you want to find the condition for no dispersion, at least in a finite bandwidth. Okay, this is given by, so if your parameters are RL and GC, you can show that RC, if you make RC equals GL, this gives you, okay, no dispersion. What is your delay? Is nothing but LC, okay. This is for your lumped LC. If you have a transmission line, sorry, oh, what happened? If you had the original transmission line with per unit quantities, as you go along the distance, right, along the transmission line where the length is Z, your delay is actually root LC times Z. Okay. In this case, if you use lumped elements, it will be root LC. Okay. The last thing to remember is that once you have decided to go to lumped elements, now there is automatically a bandwidth limitation. Okay. If you had transmission line with per unit quantities, it's a completely distributed system. Okay. So there is no bandwidth limitation. However, even if you had ideal LCs, lumped LCs, we know that at some frequency, it is going to be, capacitance is going to become a short, it's going to be dominated by the inductance impedance. Okay. So you can find an expression for the input impedance of your LC. And you can show that so you actually have a cutoff frequency, and the cutoff frequency you can find out when this term goes to 0. Okay. So beyond this, you can't use the transmission line. So this is one bandwidth limitation if you use lumped elements. Okay. So where would these kind of amplifiers be used? So you typically use it in cases where power is not a concern, okay, because these kind of distributed amplifiers are very power hungry. Okay. The other thing to remember is the noise figure of these amplifiers will also be very high, and obviously area would be very high. Okay, these three things. So in cases where these things don't matter too much, you can definitely use them. And typically, and they're definitely used. Okay, not very often in CMOS systems, but there are other applications where you might have gallium arsenide, okay, implementations of these kind of amplifiers. Okay, okay. So we'll stop here for today's class, and we are going to meet tomorrow morning. Remember that. Okay. So tomorrow I was thinking